What is the main problem addressed by the proposed method in the paper?
The main problem addressed by the proposed method in the paper is the inefficiency of next token prediction in acquiring language, world knowledge, and reasoning capabilities. The paper argues that current state-of-the-art next token predictors require orders of magnitude more data than human children to achieve the same level of fluency. To tackle this inefficiency, the paper introduces a novel approach of training large language models, LLMs, to predict multiple tokens at once, termed multi-token prediction. This method aims to drive the models towards better sample efficiency by instructing them to predict n future tokens from each position in the training corpora simultaneously and in parallel. By implementing multi-token prediction, the paper aims to improve the performance, coherence, and reasoning abilities of LLMs beyond the limitations of next token prediction.
How does the proposed method work? Please illustrate it step by step.
The proposed method works by training large language models, LLMs, to predict multiple tokens at once, instead of just the next token as in traditional next token prediction. This is achieved by implementing a multi-token prediction task where the model is instructed to predict n future tokens at each position in the training corpus simultaneously. The model employs a shared transformer trunk to produce a latent representation of the observed context, which is then fed into n independent output heads to predict each of the n future tokens in parallel. This approach allows for more efficient training and inference, as it reduces the GPU memory utilization by carefully adapting the sequence of forward and backward operations. By predicting multiple tokens at once, the model is able to capture longer-term dependencies and patterns in the data, leading to improved sample efficiency and faster inference times. Additionally, the multi-token prediction architecture enables self-speculative decoding, which further speeds up inference by allowing the model to make multiple predictions at once. Overall, the method enhances the performance, coherence, and reasoning abilities of LLMs by training them to predict multiple tokens simultaneously, thereby improving their overall efficiency and effectiveness in language modeling tasks.
What are the theoretical benefits of using multi-token prediction over next token prediction according to the paper?
The theoretical benefits of using multi-token prediction over next token prediction, as outlined in the paper, include improved sample efficiency, enhanced inference speed, and better long-term pattern learning. Multi-token prediction allows models to predict multiple tokens at once, leading to better sample efficiency by reducing the amount of data needed for training. It also enables self-speculative decoding, making models faster at inference time. Additionally, multi-token prediction promotes learning longer-term patterns, especially evident in extreme cases like byte-level tokenization. The paper demonstrates that multi-token prediction leads to stronger gains in various tasks, such as coding and natural language models, compared to next token prediction. Overall, the key theoretical benefits of multi-token prediction include improved efficiency, faster inference, and enhanced long-term pattern learning capabilities, as supported by the experimental results and analyses presented in the paper.
How is the GPU memory utilization reduced in the proposed architecture for training multi-token predictors?
The GPU memory utilization is reduced in the proposed architecture for training multi-token predictors by carefully adapting the sequence of forward and backward operations. In the architecture, after the forward pass through the shared trunk, the forward and backward pass of each independent output head is sequentially computed, accumulating gradients at the trunk. Logits and their gradients for the output head are created and then freed before moving on to the next output head, requiring long-term storage only of the d-dimensional trunk gradient. This reduces the peak GPU memory utilization from ONV plus D to OV plus D at no expense in runtime. This approach allows for efficient training of multi-token predictors by minimizing the memory overhead associated with materializing all logits and their gradients, which can severely limit the allowable batch size and average GPU memory utilization.
What were the results achieved in experiments with multi-token prediction on natural language models?
The experiments with multi-token prediction on natural language models showed that models trained with a 4-token prediction loss outperformed the next token prediction baseline in terms of Rouge LF_1 scores for summarization tasks across different training dataset sizes. Specifically, the 4-future token prediction model demonstrated improvements over the next token prediction baseline, with the performance gap decreasing as the dataset size increased. Additionally, in natural language mathematics evaluations, the 2-future token prediction model performed on par with the next token prediction baseline throughout training, while the 4-future token prediction model experienced a performance degradation. The results indicated that multi-token prediction training led to enhancements in generative evaluations, such as summarization, showcasing improved performance and efficiency compared to next token prediction models across various natural language tasks.
What are the reasons behind the improvements in downstream performance of multi-token prediction models, according to the experiments discussed in the paper?
The improvements in downstream performance of multi-token prediction models are attributed to 2 main reasons based on the experiments discussed in the paper. Firstly, multi-token prediction allows models to learn transferring information across sequence positions, which facilitates the formation of induction capability and other in-context learning mechanisms. This leads to qualitative changes in model capabilities and generalization behaviors, especially for small model sizes, enhancing their ability to complete partial patterns by predicting the most likely continuations accurately. Secondly, multi-token prediction promotes algorithmic reasoning tasks by improving the model's capabilities to reason more effectively in context, surpassing the performance gains achieved by simply increasing the model size. This is demonstrated through tasks like polynomial arithmetic, where multi-token prediction leads to significant improvements in out-of-distribution generalization, showcasing the model's enhanced ability to handle complex reasoning tasks. In essence, multi-token prediction helps models focus on predicting tokens that are crucial for the remainder of the text, reinforcing their decision, making it critical choice points, and enhancing their overall performance on a variety of tasks.